Welcome back, everybody, to Engineering 443. This is officially our 10th lecture. I hope we could spend a fair amount of time hearing what people are doing for their projects, because we're getting to a point in the class where the projects need to be the dominant thing going on. And then I want to talk a little bit about loading and running antimony models and SPML models inside of CompuCell. We started talking about that last time, but we didn't really have time to do any exercises. And I'd like to walk through that. And then there were some issues about how to do file saving, which maybe TJ could demonstrate a little bit, how to save movies and convert them into, how to save screenshots and convert them into movies. And there were also some issues with steering, and I wanted to introduce steering. When you're going to use CompuCell for yourself, the steering panels may not be that important. But if you're going to use CompuCell as a NanoHub app, and you want the people who are using it to be able to change parameter values without having to run Twit and edit the code, then you're going to have to learn how to use the steering panel in CompuCell to define parameters and change them on the fly as you run simulations. So with that, I'd like to start out by saying, so again, I'll start out as usual, their student project updates, and then we will review a little bit of the chemotaxis work. I would have liked to do it last week, but not everybody had handed in their homeworks. I'd like people to show us some of their results from last week's homeworks. In particular, the dependence of some of the chemotaxis properties on CompuCell parameter values. I think that could be interesting. So I'd like to go around the room and get some input on that. And then we'll talk a little bit about antimony and running antimony in CompuCell. Again, we talked about that a bit very quickly last time. Some people are already doing it in their projects, so it'll be a review. And some people, of course, took the class last semester, which covered it in detail. But I'll show a few of the slides from last semester just to remind the people who haven't seen it before about basics of antimony model specification. And then we'll work with the delta notch model, and Josh will help walk us through that model, and we'll play with that. And then depending on how much time we have, we will try a cell sorting model, a cell cycle model. You could download SPML models from Biomodels database and run them in CompuCell. You can also convert them to antimony, which makes them easier to read. And Josh will show you how to do that. So those are some of the topics that we're going to talk about. So let's start with the project updates. Remind you that your provisional project is due in 2 weeks. And so we've been meeting with some students about issues they've been having, but we need to make sure that everybody is making progress on this. And we'll have Giuliano show you probably next week a bit about how to upload CompuCell models to NanoHub. One thing about CompuCell, as with Tellurium, is you could always upload the simulation yourself into the general CompuCell tool and make sure that it runs on NanoHub. But if you want to package it as a NanoHub application, there's a little bit more work to do. And we'll get Giuliano to help with that. Okay, so with that, why don't we go around the room and see where people are with projects, if anyone needs help, what we can do to help out. And maybe we should start at the bottom right-hand corner. Maybe Drew, do you want to give us an update?
Yeah, sure. I'm just gonna, I'll just share a slide of some images I've got. All right. So at the moment, these are my main results that I've gotten so far for my project. And so again, this is like looking at two different methods for drug delivery to tumor cells, and the way we compare the two methods is by having different values for how how the drug diffuses and stuff. But at the moment, my values aren't really specific here yet. It's just more of having it in common with how the paper is, and that's what I'm working on right now. I was having a lot of problems, but I think I'll just be downloading Windows right now. I think it was the problem with just having CompuCell on Linux. But also my other main thing this week is getting this project on NanoHub as well. But otherwise, it seems to be working how I would expect it to.
Also, could you maybe tell us just a few words about what we're seeing on the screen?
Yeah.
And
Okay. So I've got this drug here, for example, that's being secreted by the medium cells. I don't want it to be continuously secreting here, I don't think, but I've got it. It's coming from the medium and seeing how far it gets into this big blob of cells here, which is the tumor cell. Well, the tumor itself, and then I'm measuring with like this plot here how much each of these cells uptakes, because this is I don't know, a plot that I need to have to mimic from the paper so that I can compare the two different drug deliveries. But this is just mainly a diffusion project.
so the cells are frozen to begin with, at least they're not moving.
Yeah. In this case, and they're frozen. Another thing that the paper has, if I can find it somewhere, figures. I don't know where it's at. Here we go. Is on some of these 2D plots, you can see these tumors have different, I don't know, position. Like the cells are, the tumors kind of torn up in some places, and it's not that the drug is doing that to the cells. That's just a different configuration for the start. So I do want to get that working as well. But the cells are mostly inert.
Okay, and you were having some issues with the graphics. Maybe TJ, you could show those, and maybe TJ could comment on that.
You want me to show the issues I was having with the graphics?
Mm.
Right. Well, actually, it's in this image here. Where if I had, I'm on the Linux version. I think that's the only version that it happens on. But if I can find it somewhere, here we go. If I have the multi-threaded setting here set to anything above 1, then I, for some reason, I can't get my my like substrates here, like my tracking fields, to display correctly. I don't know why, but I know that it's still it's still here, because in this plot I'm measuring the uptake in the cells. So I know that the drug is still there. It's just not being displayed correctly. And also I had some other problems with if there's two different ways I can run my simulation. Either I can use, from here and open in player, or I can open it from CompuCell itself, the main window. And yeah, if I open it from here, then it looks like this for some reason, which is different from how it behaves like here, for example, which is whenever I open it from, I don't know, TweEdit or whatever. But it runs faster one way and slower another way, and I seem to get different results when I do it.
You get like the simulation itself behaves differently based on how you
well,
execute it?
one thing I noticed is that like this plot right here, which is in my Python code, doesn't show up whenever I run it just straight from this main window. So it's like it's almost like it's only running the stuff that's in my XML file or something.
Huh. I've not heard of this issue. Yeah, I'll have to look into this a little bit because that's a strange behavior. So when you open the simulation from player,
If I open it, yeah, if I open it from this main window here, then it doesn't load any of the Python stuff, I don't think. But if I open it like if I'm over here and I open in player, like on the right side here, then it seems to work how it should.
Okay, and you're on Linux.
Mm-hmm.
Okay, could you email me separately with just some basic information about your operating system and all of that?
Yeah.
Yeah, so I'll have to look into this a little bit. That's a very strange behavior that I've not heard of until just now.
All right.
Was it that the cisplatin field didn't update properly when you multi-threaded it? And there was also an issue when you did 3D plots, wasn't there?
Oh yeah, there was. I don't think it'll happen here. Yeah.
That one is okay.
I think if I do it from here, open in player. All right. Oh. It's a bit slow. All right. I think it's good. All right. Actually, here it is. Yeah, so this is a 3D field of cells, but for some reason, whenever I'm looking at this tracking field in 3D, it looks.
And that's actually not, is that a tracking field or is that just the chemical concentration?
I think
amount should be a tracking field.
Amount
because
is
that should be
field.
the amount in each cell.
Yeah.
But the cisplatin should be just a chemical concentration, not a tracking.
Yeah. That's a concentration, but amount is how much is in each cell.
And but they're both drawing wrong.
Yeah, I don't know why it draws only right there.
What version of CompiCell are you using?
Let me see.
Just go under help.
Oh, is it help? .2.4.
Okay. If you do want to go through the effort to try it, you could roll back to version 4.2.3 and see if the behavior is any better.
Okay.
We have been doing some development on the 3D rendering, and this may have been a bug that was introduced during that work.
All right.
But yeah, send me that email, and if you can just include like a very brief list of what you've just described, can go and track down what those issues are.
Yeah. That's all I have.
Okay, Jeffrey, I guess you're next on the roster.
Okay, I have some slides. So first, I've been working on the time averaged plots like we talked about last week. I spent a lot of time trying to get it to run with the simulation, but I had the issue of the numpy arrays that I was saving the position and velocity in would reset every time the function is called. So it was just giving me the last values of each position that was returned and not averaging over time. And so what I ended up doing is just writing data to a file and then averaging those files, which is this picture. And I'm still going to work on the other way because I can't really write data to files for a NanoHub app. So it would just be I wouldn't have time averaged plots there. But I guess this works for other purposes, like putting something in a paper. So I'm still going to work on that this week. And since I've pretty much finished the simulation part of everything, I guess plots are more or less all I have to work on. The less fun part. This is another thing. The chemical reaction that I've been using is just one chemical species from the catalyst going to the fluid. And what I try to do is match the equation in the paper. So you have the hydrogen peroxide reacting with catalase. And so what I assumed is I could say S1 here is the catalase and S2 is hydrogen peroxide, then S3 would be the products of the reaction when they react. So the fluid has this peroxide attached to it, and the source, the catalase, has this, and I attached these flux terms to it. And when I run the simulation, there seems to be a reaction because you have the fluid with this S2. I printed out the fluid concentrations of a bunch of particles. And they seem to pick up the S1 and the S2 goes down. So I assume there's some reaction going on, but there's no S3 and I have not been able to figure out where S3 is at. So I'm still looking at that. And
So I'm not sure how you specify reactions in Mechanica.
This is what I found in the documentation. So I'm not, I didn't ask Andy about this yet.
So does it follow antimony syntax or something else?
Yeah, yes, it's antimony syntax. However, we don't support local reactions yet.
Okay.
Yeah.
Okay, so that solves it.
Yeah.
But even if it did, the antimony syntax for the chemical reaction that you wrote up above is not quite what you wrote. So a catalyst, by definition, doesn't participate in the reaction.
Mm-hmm. Yeah.
And so if S2 were the concentration of catalyst, it shouldn't be there.
Correct.
It would show up in the rate law, but not in the reaction itself.
Okay.
Yeah.
And then you would have two S1. If S1 is hydrogen peroxide, you'd have two S1 on the left going to two S2, which was H2O, plus S3, which is O2.
Uh-huh.
And
Okay.
so the reaction would look exactly like what you have where you say reaction from paper. You wouldn't have, what you have here is two chemical species, S1 and S2, combining to make one molecule of S1 plus one molecule of S2 combining to make one molecule of S3 at a rate that depends only on the amount of S1.
Okay.
In particular, if you, in that reaction, if you wrote it in antimony, and you had more S1 than you have S2, the amount of S2 would go negative.
Okay, yeah.
So,
This is
so, but if it doesn't work, if it doesn't work, then that's a whole other question too. But just for the, we'll review very quickly antimony syntax for people who haven't seen it before
okay.
today. So that's okay.
Okay, yeah.
So if you wanted to do that chemical reaction, then you'd actually have to go in by hand and calculate the rate of change for each species in your Python code at the moment, I guess.
Yeah, so this
Yeah, but we actually don't really need a reaction yet. I mean, it's good enough so that we get a flux of material from the catalyst to the objects.
okay, yeah. Yeah, this is just something I was messing with. So yeah, if it's not important, I don't need to focus on it. And then this is oh yeah, in the paper they have. So we also have the slice plane now. It's easier to see what is going on here. And then there's this little white ball. And the only forces acting on it are the is a potential between it and the an interaction potential between it and the fluid. So there's no chemicals or buoyancy force acting on it. And you can see it's kind of slow down here, but eventually it will move over and get up here.
Oh, cool.
Pushes.
Oh, sweet. Okay.
And then once it gets to the top, it's a little more random which direction it will go because there is flow moving in all directions. So if it, like as it's coming up here, it's kind of moving to the side. But then it'll, I didn't record the whole going down, but it will eventually start moving down in some direction also following the
Streamlines.
flow. Yeah. So this is what I have now.
Okay, that's very nice. You made real progress on that. You're quite close to having that. I mean, if you can get the chemical reaction working, even if you have to hard code it, it's not bad to get the buoyancy from the chemical reaction. But you may not need to do very much. As Andy said, you may just say that if your cell contacts the catalyst, then it basically has its density decreases, and so you have a buoyancy force on it.
Yeah, yeah, exactly. Yeah, so if it's near the catalyst, it would just have a diffusion of stuff from there to your objects, and then as the objects move about in space, and they eventually diffuse that out, and then the decay term takes care of taking it away.
Yeah.
So probably, Jeffrey, you and Andy should meet soon. Keep talking. That's great. Okay. Okay, I guess who's next on our roster? Tyler?
Yeah, I have a few slides to share. Okay. So, so far right now, here's my flow diagram of my project in general. Right now, I have every component here implemented to some fashion. I'm still tweaking my model to in order to see the expected results in the paper. Right now, I'm coming across a few issues with the parameter values given. Right now, the parameter values for the thresholds as well as for the diffusion field are a bit unclear. And Dr. Sego and Dr. Glazier and I have been working to adjust these parameters to get the expected results. But right now I have my naive T cells differentiating to pre-activated correctly. I have just recently got the pre-activated to become activated correctly. And using the same process of fixing the parameter values, I should be able to get the activated cells to differentiate into effector cells correctly, and as well as pre-activated, activated, and effector cells undergoing apoptosis, caspase mediated apoptosis. And additionally, I have the proliferation working correctly. And I've put together a couple clips of how my model is working as of right now. And as you can see, the the naive cells come into contact with APC and they stop moving as they're pre-activated. And over here, we see that they're secreting IL-2. And once their IL-2 threshold has been reached, they turn orange, which is activated. And the activated cells should be, their intracellular TBET threshold should be reached and then become effector. And that's the same problem that I mentioned before with tweaking the ODE model. And here's the results I should expect to see. Right now, I am working on getting this red IL-2 curve to plot correctly. And after that, I've been testing this TBET curve here, and I'm starting to see it rise like this correctly. And then caspase should follow suit with its behavior. And right now, I'm seeing this correct increase of IL-2 expression, and I'm still working on getting this steady secretion line right here. But for this week until for next week, I should get this ODE model tweaked, and I should be seeing the correct results.
Okay, I'm happy to meet with you again to see if help that along.
Okay.
One thing that is important with these very complex models, this is more of a general statement, is to try to break things down into pieces. And so if you're running, for example, this pre-activation, this chemical reactions or the signaling networks inside of the cells for caspase, IR star, TBET, and so on, what you'd like to do is start out with one cell and run that model inside that single cell and make sure that what it does makes sense. And for example, for the thresholds, if you see that the level of IR star goes up to, I don't know, 5 in this case, or 7, and you want something to happen at a particular level, then you can get a sense of what the sensible levels for transitions are. And so it's important to be able to separate the model components and run them independently of each other. That can be difficult, at least to begin with, it can seem difficult if some of the information that's being passed to the signal for the cell is, for example, whether the cell is in contact with with an antigen presenting cell or not. Okay. But what you can do is have a flag, which is, am I next to an antigen presenting cell? And then you can set that flag independently of whether you actually are next to an antigen presenting cell or not. And make sure that each of the steps in your simulation behaves properly, that the intracellular chemicals behave right when the cell is running by itself, that the state transition rules work independently. And again, when you're pulling a large model, it seems maybe more complicated to break it down in pieces, but it does make it easier to debug. And so that's something to think about if you're running into problems. Of course, it's frustrating if you built the whole model to have to back off and run pieces of it independently. But it is something to think about a bit.
Okay. But yeah, that's pretty much all my updates for this week.
Okay. Let's see, Kali.
All right, can everyone hear me? Okay, great. I was having some issues earlier today. So my big goals for this week were to implement cell differentiation. And this week I was also caught up a bit with some debugging of the cyclic AMP model, which I'll get into when I actually show the code. And then I also worked on the initialization for the different cell types. Unfortunately, I promise I'll get this done. I still have to figure out how to get a local installation working on my computer. So I've been doing the initialization testing on NanoHub, but the problem is if I try to initialize all the cells, it's a lot of cells for NanoHub to handle. So I can get individual components to work, but I can't show the whole thing yet. So without further ado, let's go into each of these one at a time. So starting with the cyclic AMP model adjustments, I was noticing that as I was running the model, the cyclic AMP concentration wasn't oscillating as we'd expect. It was just increasing constantly. So that issue, Dr. Siegel will be happy to know, I think I've solved by adjusting how what's computed in the model and how we couple it to the actual chemical field. So now what we're doing, instead of having the model compute the actual cyclic AMP concentration, we're going to be extracting the function of C variable and the refractoriness from the model. And then using that to calculate the cyclic AMP the change in the cyclic AMP concentration based on what it was previously. So not much different here. We give the cell the model, we get the cyclic AMP, we get the ammonia concentration, we change variables based on cell type as needed. Now what's different is in the step function, which we get the cyclic AMP and ammonia concentrations at the beginning, we run our time step, then we're going to calculate a new C total variable, which is going to be the previous iteration of the previous cyclic AMP concentration minus this term here, which was previously found in the antimony model, but now we are directly calculating a change. So if this term is negative, that means we have an addition of cyclic AMP. And if the term is positive, that means we're going to not have as much cyclic AMP. And then to ensure, as a safeguard, to ensure that we don't have a negative amount of cyclic AMP, we're going to find the max of the total C and 0, and then secrete that value divided by the cell volume within the entire cell. So that's the difference there. And then when we run this, I don't know if you guys can see the numbers, but you'll see the cyclic AMP concentration increase and then start to oscillate around 0.6. So right now it's at 0.001, 0.1, big jump there, then 0.08, now 0.07, now 0.068, now 0.065, 0.064, 0.0641, 0.0645, so it's an increase again, 0.0639, it's a decrease again, 0.0624, it's a decrease. Now we're seeing another increase, 0.063, 0.0634, and so on. So now we're kind of seeing more of the oscillating behavior that we'd expect with the maximum cyclic AMP instead of a strict increase like we were seeing before. And then I've also adjusted the mini chemotaxis model such that cyclic AMP doesn't diffuse into the medium, because in the model it only diffuses among the cell types, whereas ammonia, on the other hand, can diffuse in the medium, which is why we see it going beyond the group of cells here. And then the ammonia is staying pretty low, I think at a reasonable concentration around like 0.01, which makes sense considering that we don't have decay in the ammonia because the model doesn't really suggest it. And the production rate is like 0.001. So over time, over all these time steps, that will continue to build. What I'm not sure is it appropriate to introduce ammonia decay, even if the model doesn't explicitly say it's there. That's a question that will probably be answered with some debugging and other analysis. All right, so that was the debugging of the cyclic AMP model.
So I have a question. When you ran the
Yes.
cyclic AMP model by itself, I mean, you're seeing oscillations, but the oscillations are very small.
Yeah.
And I thought in the freestanding model, the oscillations are very big. It goes from nearly zero to some substantial number.
Yeah, that's a good point. I'd have to check it. I'd have to run this again without the ammonia, because the ammonia impacts the cell excitability term in order to figure that out.
Okay, so maybe you think the ammonia value is different from the one that you had for
Maybe.
the other. Because I think it's important, because I think that the cyclic AMP oscillations are big. And so, I mean, the maximum value could be anything, because you can always rescale it to be 1. But it should be going for, if the max value were 1, I'd expect it to be going from 0.1 to 1, rather than from 0.99 to 1.
Right.
And so I wonder if there's still something a little bit funny about the way the model is working. And
Yeah, that's a good point. I'd have to try to run it again.
Okay, and I'm happy to sit with you and try to see about debugging that, because those can be hard. As I say, the way they wrote their original model, it was coupled in a way that made it a little bit hard to separate it. And I'd like to be able to see. Maybe can you just show the code again for the cyclic AMP model that you have?
So this code, or the string?
Start with the antimony. Let's look at the antimony. So let's see, which is the let's look at the reactions. So which one is the, so C is cyclic AMP?
Yes. And then N is ammonia.
So you have C decays. Where is C created in the first place?
C isn't created in this iteration of the string.
Okay, in the original version of the string, how was cyclic AMP created?
In the original version of the string, this first equation was uncommented. So then and the model as it was written only had a decrease in cyclic AMP. So in order to increase the amount of cyclic AMP, this term f of C plus R would have had to have been negative, which would be the case under a specific f of C condition.
Okay, so okay, so you're doing an oscillator. I mean, the concentration is always positive, but a parameter related to concentration can be positive or negative. It doesn't have to be only positive. So C is actually created by the decay running in reverse, essentially.
Yeah.
I have a question about this term and how you've implemented it currently. So doing the secretion inside of a cell on the CompuCell side, not the antimony side. So that's effectively taking the rate that would have occurred in the ODE model and instead imposing it on the PDE field. Yeah. And so my question is, when you're calculating the amount that is secreted by a cell over a single simulation step, why is the amount that's secreted different from the original term for the rate of production? I guess my question is, simply put, why do line 112 instead of line 111?
Right, because see, I thought that this here is the change in cyclic AMP. It's the the rate constant. So then if we set the total cyclic AMP to the rate constant itself, then that would just like give the change in cyclic AMP instead of, well, it would give what we're supposed to change from the cyclic AMP instead of the actual change in the value.
Well, but I think the amount that's being produced is what we're interested in, is it not? When we do a command like secrete inside cell, what this is doing is it's contributing to the secretion field of the PDE field.
Oh, okay.
In which case you're writing a field distribution for the rate imposed on the PDE field. And so,
okay.
so I think what you have in line 111 is, I think, is the actual implementation, the spatial implementation of the original ODE model, because we're interested in the rate for calculating secretion terms.
Well, I think one problem I think with the way that the paper writes these rules is that they don't distinguish the concentration inside the cell from outside the cell, do they? They just have cyclic AMP. Is that right? In the original paper of Murray.
Yeah, they just write the PDE equivalent and
Right.
don't really describe much of the details as to how they actually implemented it.
So the problem there is that you don't that they don't distinguish which part of the cyclic AMP is outside the cell and which is inside. And so if the reaction is occurring inside the cell, you don't want to secrete. If you secrete all the cyclic AMP to the outside, then the cell will stop oscillating. If you keep it all inside, then the signal cells don't signal to each other. So this is a little bit like what I was suggesting before about trying to break things up. So I would try writing the ODEs inside the cells with no chemical field outside, and make sure that the cells oscillate properly. Make sure that the chemical you showed the other day the tellurium equation in the antimony string and tellurium running, giving you the oscillations. So I would put those strings inside of your CompuCell cells, and then have them oscillate. And show that they oscillate without any chemical field. And then I'd say some small fraction, then you want either some small fraction or just read the amount of cyclic AMP inside the cell and secrete some into this chemical field, even if you don't take it out of the chemical inside the cell. You just secrete it. So you're creating chemical from nowhere. And then when you read it back, when you read it in, you add that external chemical back into the cell. Because if you secrete all of the chemical that you're producing, the concentration of the chemical in the cell goes to 0. So what do you do when you do the secretion? You do a secrete inside cell M. M equals max C tot. But you don't actually, you do change C tot because the amount you're secreting that you're thinking of is the cell dot SBML dot cyclic AMP FC plus. The amount you're secreting, where do you update? Do you ever update the amount of the chemical concentration inside the cell? Does the secretion do anything to the amount inside the cell?
Well, the values, the intracellular model parameters, FC and R,
right?
Those are coupled to the amount of extracellular cyclic AMP that the cell is exposed to. And so Kali is updating that value in the ODE model at line 104. So the ODE model gets an updated amount that the cell is exposed to. And then the ODE model is integrated one step that updates FC and R. And then there's, in turn, an updated amount of release of cyclic AMP by the cell.
Okay, so I think what's happening is exactly so I think you've got it. I think it may be so the amount that you put in that's inside the cell
Mhm.
at this point is whatever the amount outside the cell is. Right? So in line 103, you're reading the amount outside the cell. And in line 104, you're putting it into the cell. And I suppose it's probably possible to make it work that way. But I don't think that I mean, biologically, that's not what's happening. What's happening is that there's a cyclic MP outside the cell. The cell takes a small amount of that and adds it to the amount that's inside. And so I would do something, I would first take your existing old model, the model you had for the oscillator, and run it inside the cells with no secretion and absorption. And then I would say, now I'm going to say that some fraction of the internal amount, and it's going to have to be a very small one, maybe start with 0 like this, is I do secretion dot amount seen by cell is C. And then I would say the amount inside my cell in line 104 is the amount I had before plus some scaling factor times the amount from outside. So that would represent I'm pulling some small fraction of the concentration from outside into the cell. And that's going to modulate your oscillator. And then the same thing on secretion. To begin with, you assume that you're secreting so little it has no effect. And you say, okay, I have the concentration inside the cell is C. And now I'm going to take that amount and I'll secrete some fraction of that to the outside and may or may not subtract that from the amount in C. But to begin with, I would run the oscillator inside each cell independently, have it drive the chemical field and make sure that works, and then read in the amount. And so I do it in 3 steps. And I think if you do that, it will be easier to figure out what's happening. And I understand because of the way they wrote the equations, it's not so easy to separate it. But you do have those oscillators that were written in the paper where it was just the ODEs, and you showed that you got those to work. And so I would start with those. And I think if you do that, you'll be able to get it to run pretty quickly.
That's the goal.
The other thing that I don't know if that was clear. I said that pretty fast, so I'm happy to go over it again.
Yeah, we can see.
The other thing that you have access to, I believe, which could be useful, is if you look at your antimony string. If we look at your antimony string, if you gave the equation a name, cell.sbml.model square bracket E1 will return the rate. So if you had equation 47, for example, and you wanted to know what is FC plus R over 10, the reference to quote E1 close quote will give you that rate. So you don't have to recalculate it if it's in
That
the
is
end.
helpful.
So those E1s and E2s behave just like any other variable. You can reference them. And that can be very convenient. If you have a very complex rate law, having the value of the rate is very convenient. That's why naming the rates is a useful thing to do. Naming the equations is useful because the name of the equation returns the rate. We did that a little bit last semester, but not enough that I'd expect people to remember it. That's a helpful thing. And that would probably come up in some of the other projects too.
Okay.
So
I may end up scheduling a meeting with you to go over the
Great.
inside the cell, outside the cell
Great.
coupling.
So but my suggestion would be to first take the model you wrote and put it in the cells and make sure that it runs just the way it did normally. And then we'll say, okay, now the chemical outside the cell, the amount secreted is the amount of cyclic AMP inside the cell. Maybe with some threshold or something else. And then the third thing to do would be to ask the question, how does the amount outside affect the amount inside? Basically, you're going to add that amount in. Because what's going to happen is the cells that are oscillating will continue to oscillate, and they'll secrete. The cells that are excitable will send out one pulse of cyclic AMP, then they'll sit there without anything until they get pushed up a little bit by the extracellular cyclic AMP. And I wouldn't worry about the ammonia until a little later.
Okay.
I just use the ammonia as a fixed amount to begin with. And again, that was pretty fast, but I hope that we can at least give you some place to start. These are all complex models, so trying to get them to work is not true.
Okay.
Anything else you wanted to go over now, or?
Yeah. So regarding
Please, go ahead.
cell differentiation, it was one of my other goals for this week. In the discoidium model, I put it in the step function, I think, for the main steppable. The idea is that pre-stock A cells will differentiate into stock cells, and pre-stock O cells will differentiate into pre-stock A cells at a probability that is proportional to the contact area with that other cell in question. So I took that to mean that if a cell has 100% contact area with the type that it's supposed to differentiate into, there's a 100% chance that it will differentiate. And if it's 0% contact area, then there's a 0 chance. So I don't know if CompuCell 3D has like a random number generator function. Right now, I knew NumPy. So it's the uniform function will generate a random number between 0 and 1. So then I calculate the fractional contact area of our cell of interest with the cell that it could differentiate into. So in this case, it's between pre-stock A and stock cells. And then if the random number generated is less than that fractional contact area, we differentiate into the different cell type. And it's the same thing for pre-stock O cells differentiating into pre-stock A cells. That was my interpretation of the paper, because it didn't give like a threshold saying, oh, if the contact area is at least this, then it will definitely differentiate or something like that. Okay, so then that's cell differentiation. Any comments?
I have a comment, but I guess. Yes. So one thing to watch out for is double check to make sure that that the common surface area with cells divided by the cell surface makes sense, because it may calculate the common surface area using slightly different algorithm from surface. And so you want to make sure that if you added up all of the common surface area with all the cell types around it, and you're missing a square bracket in line 77. Close square bracket. You want to make sure that number adds up to 1. It should, but I would double check it. So I would actually print out that number, that fractional value that you're calculating, and make sure it looks reasonable. Again, one way to check that would be to take one pre-stock A cell and surround it by cells that are type ST, for example, and make sure that you return 1 if all of the contact is that. So those are sort of little unit tests you can do to make sure that the things are working right. And then if the one thing that you want to ask about is essentially how fast you want this transition to happen. So in this case, if my pre-stock A cell were completely surrounded by stock, I would inevitably make this transition after 1 time step. So the probability would be 100% per time unit. And that may be what you want. But the question is, what's the scaling? What's the typical time for transition? And you want to think a little bit about whether that number is right. If you using a linear function of the value gives you an exponential function of the probability, and so you sometimes have to use these Poisson process corrections. Instead of looking at the probability is num less than fract of a stalk, it might be num is less than 1 minus e to the minus fract of a stalk divided by some scaling factor. And a lot of times it doesn't matter. If the fraction of contact is small, it makes no difference. If the fraction of contact gets towards 1, it can make a difference. Although in this case, a fract a stalk is limited. It can never be bigger than 1. So it's worth thinking about that, because the typical time it takes for the transition to happen will depend on that. So you might say, well, I don't want the probability in one time unit to be 1, even if I'm 100% surrounded. Suppose I'm 100% surrounded and it actually takes me 20 minutes, 20 Monte Carlo steps instead of 1. Then the natural thing to do would be to say if num is less than fract a stalk divided by 20, and that won't quite work. And TJ's has a lot of experience of doing those kind of corrections. But the key thing is how long does it take for the transition to happen stochastically? So what's the typical time for the transition to occur? That's actually probably something you can look up. I would say there'll be experimental data that'll tell you that. And we can certainly look at the paper together and see how that's implemented.
Okay.
And the other one will be the same. The second one will have exactly the same issues about transition. Yep. Okay, go ahead.
And the very last thing I had was the initialization. So using some functions that I had found that seemed to map pretty nicely to the general shape we're expecting scaled. Again, we're dealing with a lot of cells here, so I'll demonstrate the initialization of the pre-spore cells. Wait, not this. And of course, it's going to throw an error. Oh, that has to be self in front.
I think probably the most confusing thing about Python is when do you need a self dot and when don't you?
So this is currently the initialization of the pre-spore cells. I also have the, pre-stock O cells as well that would go on top here. So I think this shows that the method of initialization seems to work. Dimensions need to be adjusted a bit, but it is giving us the shape that we want. So once I figure out what the actual simulation domain is going to be, then I have to like rescale my equations to figure out the values for the equations and then also the target volumes. But right now it seems promising. And that's all my updates, I promise.
And how big? Well, it's fine. I mean, as I say, at this point of the course, the most important thing is to help you get through the project. So if there's more to discuss, that's fine. We take the time we need. How big are the cells in voxels? I mean, how many voxels does a cell occupy in your simulation?
Target volume for pre-spore cells is 30.
All right. Let's see. I guess Fanbo, you're the last today.
Okay. So basically, for last week, my my general task is to wrap the Jupyter code with the Mechanica. So it is fully embedded in a black box. So the user do not have to know anything about the widgets in the Jupyter. So they can run code. So I will very quickly show how does that work. So I pretend I know nothing about the Jupyter widgets, and I just open the Jupyter book or the Jupyter server in NanoHub. So I have a code. Let me find an example code. For example, the bounded C latex code. So this code can be run locally, like in the machine. And I just copy it and paste it in the Jupyter notebook and just run it. And you can see it on, it can be shown like in the Jupyter notebook. And of course you can play with it and you can hit run and pause for that. So, so for this, I think it's, so let's switch to another example maybe, because I always use these examples, like maybe the Poisson ones, I think Jeffrey uses. Yeah, it is. And so the m.run here just run like the simulation. So I have to set kernel. So I'm just delay this one. I don't want to run it. So if I run it, so it's initialized the cells and it's pretty slow. I don't know why. So this is the initialization of the Poisson box. You hit reset box. And you can type the m.run to run the simulation, of course. If you hit m.run, you can see the simulation is running. And of course, you can hit a pause to interactively like pause the simulation and hit run again and pause. So, and if the user want to play with it in the Jupyter notebook and they want to like create like some cells inside the empty simulation box step by step, I would maybe like write some guides to let them know like what they have to do is they only have to like just separate their code into two cells. The first is to initialize an empty box. So if I hit enter, it will just initialize an empty box and nothing is in it. And in another cell, they can just copy the code they have, and of course they can create this, like they can type it step by step, and just copy all the code inside it. And you can see it's automatically generating like inside the our empty box. And of course you can hit run to run simulation. And of course you can reset the simulation box by hitting reset. And if you hit again, okay, it will do it again. It will just do initialization again. So I think it's a very convenient way like for them to play with like all the things in the web-based Jupyter notebook. So for and for the third task, because I would like to let different users to do like different pip install dependencies. So basically it's very easy because you just have to add in the setup file, just add an extra require here. So the user can just specify when they try to pip install the Mechanica, they can call an extra argument which says you have to install the Jupyter, and it will capture all the Jupyter for them. So the task for next week is based on like, because recently like Andy developed like a clipping plans. So the clipping plans can just clip the simulation blocks into 2 planes, and the user can select one of the planes and moves all the things. So my task is trying to like create it interactively in the Jupyter box to create some like more functions rather than run, stop, and pause, and also add like a clipping pans and trying to move things. And how does that work? I think Andy can explain it more in detail if Andy want to. Like,
Yeah, sure. Which part?
like the clipping pans.
Rendering.
Oh yeah. Yeah. So basically.
But before you start there, I have one very small suggestion, which is maybe it should be easy to display the time in the window, so that as the simulation runs, the time in the simulation is displayed continually.
Yeah, I can look into that.
I guess so. I mean, it may be more complicated because you probably don't want the time to be rotating when you rotate the display. So you want it to be outside of the display box that you're rotating.
No. Actually drawing. Actually drawing that so that it doesn't rotate that part is trivial. I mean, you just like what basically all the other objects, they have their own model view matrix, and this one you just given another model view matrix. It's really simple. Doing the font rendering is slightly more complicated, but it's not a big deal.
It just watching it run, it might be. I think it would be nice to be able to have the time, know how far along in the simulation.
Yeah. I can add the outputting time as a rendered thing on somewhere in the window.
Right. I know CompuCell Player has a lot of trouble with font sizes.
Mm-hmm.
When you resize the window, the font, or when you're running on screens with different resolutions.
Mm-hmm.
For example, my laptop has a very high resolution display, and Player sometimes has trouble keeping up with that, and it gives you itty bitty fonts for some things, so they're illegible.
Yeah. I mean, unfortunately, because OpenGL it's a cross-platform framework, it's a cross-platform way of accessing the graphics processor. Actually, honestly, it OpenGL doesn't even literally has nothing built into it for font handling, unlike say Microsoft's Direct 3D. So you have to basically roll your own font rendering, and I mean it's by that it's not really write your own font renderer, but basically you have to use some third-party font rendering thing to basically grab a font and generate the glyphs from it.
I mean, I notice it also because Zoom seems to clobber some of the font rendering in CompuCell.
Yeah.
When I run Player, when I run on NanoHub, I'm okay. But when I run, say, Twit locally and I have Zoom going, it interferes with the font sizes. I guess Zoom reaches in and does things that CompuCell doesn't know about, and so
Zoom might I mean, basically, you have all of these applications and they're all accessing the GPU. And my guess is it's probably a driver issue in that the driver is not clearing out some bit of state.
Anyway, I interrupted you. I didn't mean to interrupt you. You were going to explain clipping.
Oh, yeah. Yeah, so basically,
Maybe if you want to show people, that would be good.
sure, yeah. I mean, a Fanbo showed it, but yeah, I mean, it's the user API. It's ridiculous. The user API is ridiculously simple. It's just it's m.clipplanes is a collection,
But
and
maybe you should explain why you need to do it and what it does.
sure. Okay, so why do we need clipping planes? We need clipping planes when you're looking at a, say, a complex three-dimensional volumetric simulation, and you want to make a slice of it and look inside of it, of what's going on inside of it. And what clipping planes do is basically we support up to 8 of them. But basically it creates a slice where it doesn't draw anything on one side of that plane. The rendering, yeah, and I mean, internally it's basically you have a plane equation, and in the vertex shader on the GPU, I calculate the distance between a drawn vertex and the plane, and then that goes over to the fragment shader where it interpolates, and it's probably not interesting to anybody here how the GPU works. But anyway, from the user API, there's a clip planes array, which is a live object. And if users want to change clipping planes, they do clip planes index 0 equals blah, where you give it a plane equation. And then it internally basically copies that over the GPU, and then it sets up the state there and it clips everything. So from a user perspective, it's one line. It's trivially simple. Internally, how I do it, it's pretty sophisticated that probably nobody here is interested in how it works internally. So
I'm not sure that nobody's interested, but if at some point you want to give a lecture on that material, that would be great. I don't know whether we'll have time in the remaining couple of lectures in this semester.
Yeah, sure. I mean,
but in the future, those are kind of things that I think people might be interested.
Oh, sure. Yeah. I mean, yeah. I mean, for the paper I'm working on right now, it's good enough right now where we just do a slice. After we get this paper out, I want to do some nice enhancements where actually capping the surface of the object, and there's actually some bits of subtleties of how to do that on the GPU and handling all the edge cases and making it look good. So that's a thing in and of itself, but I'm holding off after we get the paper out. Right now, it's just a plain slice, and it's good enough for now.
All right. Anything else we should discuss about projects before we move on? No. So let me reshare the screen. I mean, given what people are doing for their projects, a lot of what I'm going to be saying today is review. So I appreciate your patience. But just come back to what we covered last time. Last time we talked mainly about chemotaxis, the idea that the cell in a chemical field, if you want a cell to move in response to a chemical field, you have to apply a force to it. CompuCell applies forces essentially by calculating effective potential energies. We need to remember always that when a cell is responding to a chemical field, it's not actually having a force applied to it. It's behaving as if it had a force applied to it. That's one of the reasons that these CompuCell things called Hamiltonians are called effective energies, because they're behaving as if they were energy terms, but they're not really energy terms. And then we did the dependence on parameters of chemotaxis. And some people had some very nice homeworks on this. And I was hoping that maybe at least a few of you would be willing to share one or two of the things you found when you varied some of your parameters and calculated, for example, we calculated velocity versus lambda chemo in class. And we showed that for a small lambda chemo, the velocity increases rather slowly, that there's a regime where lambda chemo here went from about 2 times 10 to the third to about 10 to the fourth, so factor 5 or so, where the velocity increases linearly with the chemotaxis parameter. And then for a larger lambda chemo, the velocity of the cell saturated. The cell didn't go any faster as we increased the lambda chemo. What we would, of course, like in an ideal world is that the velocity was proportional to lambda chemo, independent of whether it was small or big. And so seeing that tells us that if lambda chemo is too small, the cell is going to move randomly. It's not going to respond very much to the chemical field. If lambda chemo is too big, we run into the speed limit in CompuCell, and we can actually see directly that there's a speed limit, which is about 0.24 voxels per Monte-Carlo step. And we would like to stay below that. So typically we have a rule that we don't want cells to be moving more than about, I'd say ideally a 1/10 of a voxel per Monte-Carlo step, but in practice, 1/5 of a voxel per Monte-Carlo step. And so if we were to think about, I was trying to think about the best way to present this. If you're thinking about how to set the length and time scales in CompuCell when you're doing a simulation, the first thing that you need to do is decide how many cells you want to simulate. You're going to simulate 100 cells, 10 cells, 1,000 cells. You probably can't go over about 50,000 cells, practically 100,000 cells, maybe. How many cells you want to simulate. And the next thing you have to decide is you're going to simulate in 2 dimensions or 3 dimensions. We saw in the presentations today that if you simulate in 3D, you could do it very easily in CompuCell because it's intrinsically 3-dimensional, but it runs much slower because execution time in CompuCell is essentially proportional to the number of voxels. And so if I'm on 128 by 128 by 128 lattice, that has the same number of voxels. Well, I should have picked something that's a square. If I'm on a 64 by 64 by 64 lattice, that's the same thing as being in 2D on an 8 times 64 by 8 times 64 lattice. And so I can do a lot more, a lot bigger lattice in X and Y extent if I'm in 2D. Of course, I don't have to have things be symmetrical. If I have a thin object, I could be on a 128 by 128 by 10 or 128 by 128 by 16 lattice, if it was practical. But the first thing I have to do is how many cells do I need? Second thing I have to think about is am I 2D or 3D? And the next thing I need to think about is what the spatial resolution that I'm going to need is. In reality, in practice, you can't get away with cells being much smaller than 4 voxels in 2D. And if you're going to move around, you really need them to be at least 8 or 10 voxels if you want them to behave well. In 3D, the smallest you can do is 8 voxels, 2 by 2 by 2. And in practice, you need something bigger than that, like 32 voxels. And so that sets the minimum length scale. If you know that the cells are, you can always do more detail than that. It'll run slower, but it'll also give you smoother simulations. And if you need subcellular detail, you're stuck. You have to have more smaller voxels. And so typically we're going to run simulations where the cells might be 10 microns across, and we'll pick a voxel that is, if the cell's 10 microns across, and our voxel size is 1 micron, then the cell will typically be on the order of 60 or 70 voxels in 2D. If we picked a voxel size of 2 microns across, our cell would be on the order of 20 voxels in 2D. If we picked a voxel size of 3 microns, then we'd have a cell that was on the order, again, for a 10 micron across cell diameter cell. Then we'd have something that had 4 or 5 voxels. So the biggest our voxels could be, if we wanted 10 micron cells, would be to have them be 3 or 4 microns across. That would be the most we could do. Once we picked the length scale and the size of the simulation, then we need to look at what one Monte Carlo step represents. And in principle, we can make the Monte Carlo step as small as we want in real time. But what we can't do is make the Monte Carlo step too big if things are moving. If we only have chemical diffusion or subcellular chemical reactions, then we could make the Monte Carlo step be anything we want. But if we're actually using the POTS simulation and cells are crawling around, we run into what we see in this simulation that I'm showing, which is that there's an absolute speed limit of about 0.25 voxels per Monte Carlo step. And so if our simulation has a voxel being 1 micron, that means that the most we could do is 1 micron per 1/4 of a micron per Monte Carlo step. So suppose that the cells move at 1 micron per minute, then that would be that the biggest our Monte Carlo step could represent would be 1/4 of a minute, would be 15 seconds. And so the velocity of the cells will limit the size of the Monte Carlo step. We can always make this Monte Carlo step smaller in real time, but we can't make it bigger. And so the fastest crawling cell in your simulation will set the scale of the Monte Carlo step. And I can put that in writing, but I hope walking you through that verbally will help a little bit. So I wondered, is anybody willing to show some of their results? I know some people had some very pretty results for this problem from their homework. Josh, do you want to call on somebody?
Maybe Jeffrey or Fambo can show some of their results.
Are you willing to show some of your results for the chemotaxis problem in the homework from last week? Fambo, are you there?
Yeah, so I'm just finding like the homework.
I realize I put you on the spot a bit, but we were looking at the homeworks and they were so pretty. We thought it would be a pity not to have people share some of their results.
So I think that is what I have is, I kind of forget what the question says. So but basically when you try to increase the lambda volume, the velocity will decreases linearly as you increase the lambda volume. If you, yes, this is when you increase the cell size and trying to divide the cells. I'm not sure if but the general fact is the velocity will decrease when the cell size increase for the average velocity.
So let me understand that. What you say cell size, but do you mean the number of cells?
Yeah, the number of cells in the.
So is the total volume the same? In other words,
no.
Is each cell the same size as the original cell? So I have a cluster of cells that the volume, the number. So there are two ways you could do that. When the cells divide, each cell has half of the volume before, in which case the total volume stays the same, almost. Or each time the cell divides, its target volume is what the original one was, in which case the cluster gets bigger and bigger and bigger. And I wondered which one you did there.
I think the second one, like I make the cluster bigger and bigger by increasing the target volume by 25 when the cells try to divide. And
so the cell size is the same each time, but the number of cells in the cluster is changing.
yes.
Okay. And so in that case, I guess I might expect that to have a relatively weak effect on the chemotaxis. But one thing to do would be to plot, just to have no division and have the target volume go up. Maybe somebody did that. But Josh, we should be writing down a list of these things to explore in more detail.
Yeah.
We had a few, but we could think about some more.
Right. We did the target volume increase last class and showed that it had no effect on the chemotaxis.
Not a lot. The lambda volume is interesting because one of the things in CompuCell is that these materials are fundamentally fluid-like. And if you want things to be more rigid, the easiest way to make them rigid is by making that lambda volume term. We have the option of freezing cells. If you say a cell is frozen, it doesn't move at all. But if you want the cell to be able to move, but not very much, the easiest way to deal with that is to say that lambda volume is big. But the question then is how big? I gave you some ideas about how you can set time scale and length scale. But with lambda volume, and you want to say, I want to make lambda volume so the cells move slowly, I don't have a simple rule of thumb for telling you what lambda volume to pick. And so this kind of experiment, which we did where you sweep a parameter and see how a particular output changes, is a very powerful way of calibrating simulations. And so, for example, I think, Kali, you had a question about how do I decide what a value should be. And there were other people who also have made a comment about how do you pick a value of a parameter? And ideally, you know what these things are because somebody's measured it or told you what it is. But if they haven't, very often you know what you want the output to be. You want my cell to take 2 20 Monte Carlo steps, which represents 40 minutes, for example, to differentiate. You want the speed of the cell to be 10 microns per hour, which is 4 voxels per Monte Carlo step. I mean, 4 voxels per 100 Monte Carlo steps, something of this kind. And then you do what's called sensitivity analysis, which is what we've been doing here, which is you take the parameter, you run the simulation long enough to measure the thing you care about, in this case, the velocity of the cell in the chemical field. You measure that, then you change the value of the parameter and you measure it again. And you do a sweep where you change the value of the parameter over the range of interest. And then you look at that and say, gee, I want the velocity of the cell to be 0.15 voxels per Monte Carlo step. Therefore, I can read off in that graph the value of lambda chemo I need. And that's called backing out a parameter. It's not the most elegant way of doing things. If you have a lot of parameters, it's time consuming. But very often that's what you have to do. And it's called a sensitivity analysis. And in a sense, this is the first real sensitivity analysis we've done in this class. And I think it's worth noting that people do that all the time when they do simulations. It's something people use regularly as a methodology. Okay, did someone else want to show? Does anybody else have a result from the homework that they're willing to show us? Josh, was there someone else who wanted to hear from?
No, I mean, if anyone else wants to show the results, but yeah, I think Fambo discussed the main ideas.
Tyler, did you do any sweeps that were of interest, or?
My results were a little, they were similar, but they weren't very pretty. I'm not sure what I did wrong, but I explained it in my homework, the problems I had.
Okay. Just again, I wanted to give people the opportunity to showcase their results. All right. So, and then we also looked at adaptation, where, and this perhaps is something that should be built into CompuCell into the plugins, which is that we found that if we had an exponential gradient of a chemical, that the cell didn't move very rapidly at all, or not at all, when the concentration was low. And then when you went to higher concentrations, the cell moved too rapidly and even could get squeezed out of existence. And so what you would like is to be able to have the velocity of the cell depend not on the concentration gradient directly, but on the gradient divided by the average value of the concentration over the cell, which is called perfect adaptation. And that's how our visual systems work. Our ears do it a little bit, although not as effectively. And a lot of biological measuring systems do this, where if you want to measure small changes, you have to measure small changes around the current mean value. And that means you have to continually adjust your sensitivity, because the light intensity coming into our eyes differs by a factor of 10 to the fourth or more, depending on whether it's nighttime or bright sunlight. And our eyes actually manage that by changing the amount of photoreceptor in the retinal cells. It's actually a very inefficient process in our eyes. One of the reasons dark adaptation takes a long time is that you're actually synthesizing photoreceptor. And so the simplest way to do that with chemotaxis is to measure the concentration at the center of your cell and then divide the lambda chemo by that concentration. That way, if the chemical concentration is very large, lambda chemo goes down. If the chemical concentration is small, lambda chemo goes up. And you don't divide just by the chemical concentration, because that has the risk of the concentration being zero and getting a divide by zero error. So you divide by 1 plus the chemical concentration, assuming that the concentration is larger than 1. If what you need is, you want your divide by 1 over 1, well, some number plus the chemical concentration, where that some number is much smaller than the typical chemical concentration. And we showed that if we made that change, here we've used 1, that in fact the velocity of the cell is linear in the gradient, even though the gradient is exponential. You'll notice that there's a limit to that. When we get too far to the right, the cell will stop moving. And so there's some limit below which the cell can't read the concentration. And actually, in the thesis of Stan Murray, dictyostelium, discoideum cells are thermotactic and phototactic, and they can see very, very small. The individual cells don't see gradients very well, but the Grex, the slug that they assemble into, is very good at seeing very small gradients. And so he did a nice study essentially showing that the aggregate of schema of the dictyostelium cells could follow very weak gradients in this way. Okay. So then we talked about trying to do more multi-scale modeling. And again, most of you have already covered, to some extent at least, what I was going to cover in this class, but not everybody. So the people who've done antimony models inside of cells, please help the people in the room who haven't done it yet. Drew and Fanbo haven't had much experience with this. The other people who took this class last semester have seen this before. And what we're going to be doing is trying to use ordinary difference equation models to represent the scales that we're not representing as cells. We built, so CompuCell has really 4 classes of model. It has the cells and the way they move, which we played with quite a bit, which is sort of the unique aspect of it. It has chemical fields, diffusion and decay and secretion and potentially some reactions, which we've seen. And then it has the ability to write these ordinary differential equation models, which can either live inside of individual cells, which we've seen, or can be attached to the simulation as a whole to represent what's going on outside of the cell domain. And this is a graphic that shows, you imagine you have an ordinary differential equation model of blood flow in the body, a little CompuCell detailed cellular model of blood flow in a little piece of the liver, and then inside each one of the liver cells, you have a model of metabolism. And so that kind of model can be built into cells individually. This is a model of cell cycle, which I hope will run today, depending on how far we get. And you can then have the chemical concentrations inside of cells do the kinds of things Kali was talking about, which is be controlled by the chemical concentrations outside of the cells, at least affected by it. And you can also have the cells secrete or absorb into the extracellular environment. In this case, the cells aren't secreting or absorbing anything. They're just doing their thing in terms of growing and dividing. And I showed this simulation, which was an old simulation now, but a relatively detailed one, showing all 3 of these scales at once. On the left, we see the cells. The cells are being created by cell division at the bottom. They're differentiating, which we've seen how to do. When they differentiate, they change their mechanical properties, and so they start rearranging. That's cell sorting, which we've seen before. And in the middle, we have our diffusing chemical field. So that's our PDE solver. And each one of the cells in turn is running this intracellular model, which is reasonably complex, which represents the 3 chemical oscillators that are present in this particular type of cell. Not shown in this model is how the cells differentiate. The cells differentiate by looking at the chemical concentration. When the chemical concentration goes below some threshold, the cells then read the concentration of these chemicals that are oscillating and say, which phase of the oscillation am I in? Am I in the period when one of these particular oscillations is increasing? Am I in the period when it's decreasing? That would give me 2 phases. It actually asks the third question, which is it looks at the concentration of two of the oscillators and asks the relative amplitudes of the two oscillating species relative to each other. That defines not two, but three subregions. And you'll notice they differentiate into blue, green, and red, depending on those two concentration and their ratios. And so this is perhaps the clearest example of how these three levels work together. We're going to be playing with delta notch signaling. We've seen this before. We'll work with it today. And this is one of the classic patterning mechanisms that you have in early developmental biology, and it happens also in vascular development. And it's one of the standard patterning mechanisms of early development. We talked a little bit about how to implement these dynamic networks. Early on, we had used these SBML, System Biology Markup Language models. SBML is a nice language for model specification, model exchange, because a lot of different software tools will read it and know how to interpret it. It's not so good as we saw for humans. The disadvantage of using SBML for model specification is that you have to have an editor for it. And so we then, TJ implemented antimony model specification, which people have been using. And that allows you then to write your model specification in line with everything else in your Python. You can also put it into a file if you like as well. And so to remind you, this is again going to be a review for people who've already used this, but some people haven't, how to load and run antimony or SPML model in CompuCell. First, you have to have model specification. If you're using SPML, you're stuck. The model specification has to be written using SPML editor and then written into a file, and you'll tell CompuCell to read the file. If the model is written in antimony, you have two choices. You can also read it from a file, or you can put an antimony string into the CompuCell Python and load it into your cells. Once you've written the model string, you have to load it, and you can load it into one or more cells or into the model as a whole. You're allowed to have more than one antimony or SPML model at the same time inside objects. Then you have to build a time step the model. Then you have to know how to read and write the values in the model. And it used to be rather complicated to do that. These days, it's pretty simple. If the cell, you just use a dictionary. We'll come back to that in a second. So the first thing, and this is a review for some of the people in the class, for Drew and for Fanbo, who didn't take last semester. It's a fly-through last semester. Antimony is a model specification language. It's designed to be easy to read and write. And what we're trying to write typically are things that look like chemical reactions or ordinary differential equations. And we're going to be defining these models in the form of strings. The disadvantage of having everything in the form of a string is that if there's an error in the string, the errors that are returned may or may not be informative. So what will happen when you load a model string is that there will be a parser which is applied to that model string. And if that parser fails in some way, it may not give you an informative. Sometimes it gives you an informative error message, sometimes it doesn't. And so debugging these antimony strings is not always trivial. And just to remind you of the syntax of antimony string specification, I'm going to write an exceedingly simple chemical reaction, which is substrate T in this case, this is actually probably representing infection dynamics. T goes to I1 at a rate beta times T times some extracellular virus concentration in this case. And that arrow diagram, which is a typical way to represent reactions, turns into a rate equation. In this case, I've named the rate E1 colon T goes to I1, and then the rate. And so one of the things that's nice about antimony is that it tries to make the model specification as similar to what you draw in an arrow diagram, transformation diagram, as possible. And the only thing that you have to know at the moment is you're going to put your model specification into a string, and the triple quotes can either be single or double triple quotes. They have to be the same. You know about antimony is that one of the things about antimony is that some of its conventions are somewhat different from those for Python. And so, for example, exponentiation in one case is double star, and in the other case is a caret. The comment character is different from antimony and Python. Python, we're used to hash for comments. Antimony uses the double slash for comments. Antimony is sort of C++-like syntax. It uses a semicolon as a delimiter. And you don't need carriage returns, although you can use them. So you could write your antimony string as one long line with no carriage returns in them. But you do need the semicolons as delimiters. And the colon represents a tag name. And so we'll come back to that in a second. So here, equations, parameters, in my line, a statement here, I've defined the units of the parameter. And so by naming the equation, I make the rate rule available to me as a variable. Okay. Of course, in most situations, I'll have more than one rate law. And I might have, but wouldn't show up in the arrow diagram because the catalyst isn't used up. The diagram is either created or destroyed. If it's not created or destroyed, if it's just regulating the rate of something, it'll show up in the rate side, but not geometry. It's not always true that we just have one molecule of C, giving me 7 molecules of C. Or if I really want to write my catalyst, I might have 1 molecule of A plus 1 molecule of the catalyst, giving me 2 molecules of B plus 1 molecule of the catalyst back. That's a legal thing to write, in which case the catalyst doesn't do anything in the reaction. For each chemical species, on either side of this arrow diagram, I get a separate rate, I get a separate ODE. So if I have A on the left, I'm going to get an ODE for A. If I have B on the left, I'll get an ODE for B. If I have C on the right, I'll get an ODE for C. Notice in the equation I wrote here, 3A goes to 1A. I destroy 3 A's for each reaction, I create 1. So my net -2. One thing that antimony does carefully is that it keeps track of how many of each molecule are created and destroyed. That's called stoichiometry. And that's quite convenient if you're writing complex chemical reactions. Again, notice that the exponentiation operator is caret in antimony. It's double star in Python. So that's that's easy to make that mistake. The second thing is that sometimes I have sources. Nothing goes to A. And that would be equivalent to just writing dA by dt equals K. Or I could have decay. A goes to nothing at a rate K times A. that would be equivalent to writing dA by dt equals minus k times A. So you can have nothing on either side of an arrow. We can also have $, which defines fixed concentrations or boundary species. We won't use that so much inside of CompuCell. And I'm not going to go over all the details of antimony. That's quite elaborate language. I'm just going to give you the basics for what we need for this class. It's also allowed to write ordinary differential equations directly with a prime. T prime equals beta times T times V is exactly T prime is equivalent. It's the old Newtonian notation instead of Leibnizian notation for derivatives. dt by dt equals beta TV, equivalent to that. But that's equivalent to writing the same thing would be arrow goes to T at that rate. So there are two different ways of writing the same thing. Notice that the rate, beta times T times V, looks the same, but the left-hand side, arrow goes to T or T prime equals, is different. If I have the same species or variable in multiple reactions, antimony will automatically sum everything up. So if I have, let's see, nothing goes to T and T plus V goes to I1, then my T equation will be, I'm creating T at a rate K0, I'm destroying T at a rate K1 times T times V. So they'll both show up together. And so the way you distribute the specification of reactions is a little bit different from the way you'd write ODEs. Here I have 3 arrow diagrams giving rise to 4 rate equations. And so I have to learn a little bit how to convert those back and forth. Any parameters in the model, beta, V, and so on, have to be specified. If you don't, the parser will choke. And variables don't have to be specified. If you don't specify their initial values, they'll be defaulted to 0. But you should always specify the value. One thing that's a little bit complicated to get used to in antimony is that the code is not executed in a linear fashion every time the antimony string is run. The antimony string is parsed once. It's converted into an internal representation. That internal representation is run. And so in particular, if I write something like T0 is equal to 1 e to the 7th, T equals T0, that will assign the initial value of T to be 1 e to the 7th. But if I go in later and change the value of T0, it does not change the value of T. So regular equal signs are read only once at the beginning of the simulation, or when the model is read in the first time, and they're not updated. And there's a different kind of equality, colon equals, that tells you that you have to continually update the relationship. And so just the way we sometimes have to remember in Python, whether we need a self dot, the thing that the bear in antimony is remembering whether you need a colon equals or an equal sign. Antimony allows us to define functions. I'm not going to show you how to do that here. I sent around the cheat sheet, which explains how to do it, and events. Kali showed some events, and we may get to some events a little bit later. In general, we won't use events very much inside of our ODE models. We'll use the Python layer of CompuCell to do most events. The functions we'll use. The next thing we do is load the model as a string. we can do that either into a free-floating model or into one or more cells. And I showed these pictures before. There are two kinds of commands that allow me to load an antimony model into a particular cell. This could also say SBML model instead of antimony model. I can either read from a model string here. I give the model a name that's required. I say which cell I'm loading it into, and I can also define the relationship between Monte Carlo steps and antimony time using the step size. I can load it into a bunch of cell IDs if I'm specifying by ID. I can load it into all cells of a given type, which is very useful. Or I can add it to the model string as a whole, the model as a whole, or the called free-floating model. And so those are my options. Then I time step the model, and at the moment, all the models move in lockstep. I can have different, each model I load can have a different relationship with MCS to internal antimony time. But each time I call step, time step SBML, it will advance each model by whatever internal units it defines to be one Monte Carlo step. And so self.timestep SBML will advance all of the SBML models, free floating inside of cells, however many you have, by one Monte Carlo steps worth of time. And so that's a simple function. There are a variety of ways of setting the integrators and the other things that you can do in antimony and tellurium, which I'm not going to go into now. You can look them up, but you can set all of the integrator options. And then to read and write variables, the syntax is almost the same for free-floating and cell-bound models. For a free-floating model, I use self.sbml, the name of the model, because there might be more than one, and then a dictionary entry, which is keyed to whatever the name of the variable or model was. So if I named a chemical rate equation E1, quotation mark E1, close quotation mark, would give me the rate of the equation E1. If I had a variable T, quote T, close quote, would give me the value of T. If I had a parameter K1, quote K1, close quote, would give me the value of the parameter. Self.sbml.model name gives me a free-floating model. Variable equals is to read it out. If I want to set it, I just say self.sbml model, et cetera, equals value. The one thing that you have to watch out for is that just because I set the value doesn't mean that that value does anything inside the SBML model. In the example I gave back here, if I said in CompuCell, SBML self.sbml model square bracket T0 equals 10, it would change the value of T0, but because T0 isn't read except when I load the model, it would have no effect on the simulation. And so that can be a little bit confusing, and we have to think about that when we want to change parameters. When we change variables, there's no problem. When we want to change parameters, we have to ask the question, does changing that parameter actually do anything to the model or not? Each cell owns its own copy, if it was loaded, of the model. Cell.sbml model name, square bracket, variable or parameter name, square bracket, allows me to read or write. In the old days, we had to do get and put, which you've had to do a little bit with chemical fields, for example. and with the chemotaxis parameters. Here, everything behaves just as a dictionary entry, so it makes it very simple. The one time you will have to copy parameters in and out of the SBML is if you want a tracking field. So if I create this auto tracking field, and I want the auto tracking field to show me the concentration of a molecule inside the SBML, at the moment, the tracking field can only track properties of cell. It can't track properties of cell.sbml.model. And so I would have to create, suppose I want to know the concentration T1 inside each cell, and I have a tracking field for T1, I would have to say cell.dict square bracket quote T1 close square bracket equals cell.sbml.model name square bracket T1. So that's the one time I have to actually copy things explicitly in and out for tracking. Any questions about that? As I say, Kali and some of the other people have already used this, and it's a rush through for a whole semester's worth of courses for people who haven't used it. But I wanted to go over that in some detail. And then there are a couple of convenience functions, some of which I didn't discuss. As I say, you can set the integrated parameters for the SBML. Sometimes we want to actually copy a model and its state from one cell to another. So we can basically clone an SBML model. So there's a copy, which we can do. And sometimes we might actually want to delete a model. It's not so obvious why we would want to delete a model, because you can always leave the model there and not read it or write it. But it does take time to run the simulator for it, and so we can delete it if we like. And that's about it. So I want to talk about delta notch patterning. Delta notch patterning is one of the main contact mechanisms that cells use to determine spatial patterning, local spatial patterning. It's important in development, and it's something that is universal in multicellular organisms. We have it in the patterning of the human intestinal crypts. So the way your gut is built and maintains itself depends on delta notch patterning. The way your blood vessels develop depends on delta notch patterning. The way your neuronal system develops needs delta notch. In fruit flies, the way the hair cells are positioned depends on delta notch. And in zebrafish fish, the way the eye develops depends on delta notch. So this is a very universal process. If you're interested in reading more about it, there's a very nice high-level review paper. It's a little old, but delta notch has been understood at some level for a long time in development, and there's a link here in the slide. Delta notch has, and we covered this a little bit last time, I want to just go back over it again. Delta notch has a sort of an interesting behavior. When we talked about cell adhesion between cell adhesion, most of the cell adhesion molecules, cadherins, CAMs, are what are called homophilic. That is, you have the same kind of molecule on both cells, and those two molecules like to stick to each other. With delta notch, it's more like what happens between a virus and the cell it's going to target, or between, say, a T cell and an antigen presenting cell, which is that the two cells that are in contact have the opposite type. So delta on one cell doesn't bind to delta on the other cell. Delta on one cell binds to notch on the other cell. And it can get a little bit complicated because you have delta notch on the same cell, and then they can actually bind to each other in the membrane on the same cell and then disable each other. And so you get sort of a net delta signal or net notch signal, depending on which one you have more of. But in general, delta on cell 1 binds to notch on cell 2. When delta and notch bind, that sends a signal where the notch is cut by a variety of molecular species for that purpose, and the intracellular domain of the notch then goes into the cytoplasm and can do all sorts of interesting things. One of the things that it does is go to the nucleus and act as a transcription factor. And so notch can lead to a variety of things. In particular, it could lead to either cell differentiation or cell proliferation. And so what you tend to get are patterns where high notch alternates with low notch. And so you get these not a perfect checkerboard. You get a pattern with a little bit more complexity than that. And we want to investigate that. But the basic idea is that if I have notch signaling inside of my cell, it inhibits delta. If I have delta signaling to notch, that inhibits as well. And so I have this interesting feedback loop between cells. Delta and notch within a single cell aren't interesting. It only comes into play when we have pairs of cells. And so we're going to use this very simple model of Collier, which doesn't include all the complexity of activated and inactivated species. I'm going to assume that I have delta and notch, and that the amount of delta in my cell is inhibited by the amount of notch in my cell, and vice versa. So the delta dt is equal to some rate constant. It's inhibited by notch, and d decays. D notch by dt. Sorry. Yes.
I think it should be important here to explain what the inhibition here means.
Okay, let's see. So what I have here, let me come back to this picture here. If I have activated notch, that is this NICD notch, that reduces the amount of delta in my cell. And so if I have activated notch, I decrease my amount of delta. If I don't have activated notch, I produce delta, and the delta comes up, level comes up, and saturates. So in the absence of notch, I'll have delta. By default, my cell has delta. If I have notch signal coming in from outside, I turn off my delta signal. And it's a little bit complicated to draw that in one picture. They've tried to do that here, but in fact, to begin with, you would have perhaps a picture where you show delta and notch on the cell without the cells in contact. Then you show delta and notch coming in contact. The delta binds to notch, it activates the notch, and that activated notch then turns off delta in this cell. So it's a multi-step process, which is outlined here. Initially, I have delta and notch next to each other. Delta binds to notch. The notch is cleaved. The notch sends a signal, and one of the things that signal does is disable delta in this cell. Okay, did that help at all, Josh? So maybe I should have started with the notch signal rather than the delta signal. So if I look at notch, notch is activated by the extracellular delta. It's not paying any attention to the amount of delta in my own cell. It's paying attention to the amount of delta in my neighboring cell. So if my neighbors have no delta at all, then my amount of notch is 0. If my neighbors have a lot of delta, I have delta prime to the k over a plus delta prime to the k. This is a Hill function. This will go to 1, in which case the amount of n I get will be 1. So if my neighbors have a lot of delta, my notch level goes up. If my neighbors have no delta, I have no notch. So that's the notch one. If I have no notch, this term is 0. My delta production, that is maximal, and my amount of delta will go to 1. So if my cell has no notch, if I have a cell by itself, I have no delta signal, my notch goes to 0. If my notch goes to 0, my delta goes to 1. So an isolated cell has a delta of 1 and a notch of 0. If I bring a cell in contact with cells that all have a lot of delta, that delta forces my notch up. So I go from notch 0 to notch 1. When my notch what level goes up, that pulls down my delta. And so my neighbor's delta pulls down my delta and pushes up my notch. We'll see whether that's actually what we see or not. Okay. And what we should see then is a hexagonal pattern like that. And maybe we should actually make a note. Maybe we should actually, Josh, we should probably make a slide that walks through that argument that I just made. We can look back at the notes and walk.
Yeah, that's a good idea.
Okay. Because it's not, it's, as you point out, it's not trivial. But you're right, it's better to start with notch. If you think about an isolated cell doesn't have any external delta, so this term is 0. Notch then decays, so notch is 0. If notch is 0, this is 1, and then delta goes to its maximum value. So an isolated cell has delta 1, notch 0. A cell that is surrounded by other cells with no notch, with no delta, also has delta 1, notch 0. But if a cell is surrounded by cells that have delta 1, then you wind up with notch 1 and delta 0. All right. So what we're going to do is we're going to look at a simulation where we're going to fill the space with cells. Initially, we'll freeze them, although we'll unfreeze them pretty soon. We'll put this little model in antimony. We'll add it to all cells. And at each Monte Carlo step, we're going to loop over each cell. We'll loop over the neighbors of the cell. We'll calculate what the D of each cell is. We'll average that. We'll pass that to our value, and we'll update these results, and we'll visualize the pattern. And the only things that we need to know are the rate constant for D, which we'll set to be 1, the scaling at which the delta saturates, which is defined to be 0.01, which is pretty small here, the scaling at which notch saturates, which is defined as 100. We could have made those both 1, actually. And the Hill coefficient here, H and K, which we'll set to 2. Okay, and this is what that model looks like. So initially, we're going to start, initially this model starts, this is notch. Initially, this model starts with all the cells having notch equal to 1. That's the unstable state, because we said that we expect that we're going to have low notch as the isolated cell. And then the cells begin to communicate with each other. The notch level goes down everywhere. And then random fluctuations lead to this patterning. And you'll notice that the patterning is a little bit maybe the opposite of what we'd expect. We have low notch cells surrounded by bands of high notch cells. So high notch cells can touch each other, but low notch cells never touch each other. All right. And Josh, now I'm going to turn it over to you to show them the code. And everybody, please fire up CompuCell. And Josh, I guess if you want to do this, you're going to do this on your desktop machine, or you're going to do it on.
I'll do it in my desktop, but the code is available on Canvas. The code that I'm gonna be showing is available on Canvas. I think I created a lecture. I'm gonna launch a poll. It's created. It's inside a folder called Lecture 10 Demos Lecture 10. And the first one I'm gonna be working with is the delta notch, the plain delta notch simulation. So I'm gonna, yeah, go ahead, James. I'm
I was
sorry.
going to say, if anybody has trouble finding it, please speak up. Okay.
Um,
I'm going to unshare the screen. Tell me when you're ready to take over the screen.
1 second.
So in the meantime, please launch your CompuCell installation.
Yeah, 1 second. I think just yeah, I'll download. Just 1 second. I think the version I'm not exactly sure, but I think I've been working with so many versions, but I think the version I uploaded is one version that doesn't have the XML. It has instead the everything is specified in Python. 1 second.
So if you go to lecture 8, sorry, if you go, hold on a second.
Yeah, I think I found it.
In the course materials, if you go to the Google Drive, lecture 9 demos, the delta notch there has it written out the way you need it. So
Can you post a link in the chat?
Yeah, let me do that.
I thought, yeah, the version I have does not.
Sorry, just take me a second.
Or I can just also.
Actually, the directory of student materials should be shared with everybody already, but that doesn't mean it's easy to find. So let me grab a link to this. Okay.
I think I've, yeah. So I
Okay, I'm putting in the chat a link.
Yep.
That should
And I
take you, should allow you to download that file. So please try it. Make sure you can get that.
Yeah, one second.
That was a link to the containing folder. If you would prefer to just have that one demo. I'll put that link into.
I am almost ready. It's just that I wasn't anticipating having this problem, but
Okay, was everybody able to at least get the file?
okay.
Kali was able to get it. Okay. Tyler, Drew, Bonbo, were you able to get that file to download?
So yeah, but yeah, I think this one doesn't have the XML either.
The one I shared has the XML.
I downloaded the files from the drive link you sent, and I uploaded it, and I don't have the XML either.
Huh. All right,
Yeah.
let me check. That's embarrassing. If it is, let me just take a look. See.
I also just noticed that I don't have the XML either.
Right.
All right. Let me then. Okay. What's that?
But I almost have it ready.
Wait a sec. I see. Okay. Sorry about that. Let me get this link. Sorry about that. My mistake. So here. There it is. Let me double check because my mistake, because what happened was there were two very similar file names. And I picked the wrong one. All right, here it is. Get link. All right, copy link. Yeah, try that. Okay, can you try that one? Josh, can you see if that's the right one?
Yeah, I'm shaking. Yeah, I think this one does.
Yeah, this one has it.
Yeah.
Okay, and I will put this into the class directory so that you have it in the right place. That was in the.
So one second now.
And I apologize for having it. I'll put it in lecture 9 demos. Why don't I put lecture 10 demos since this is actually lecture 10?
Yeah, that's a good idea. And I'm about to.
Then we won't have. Then we shouldn't have a problem with the collision of names if it has the same name as that older version. Okay, did that work? Were people able to run that one?
Yeah, 1 second. Let me download it.
Oops.
Okay. And
I can do it, Josh.
yeah, that one. Okay, that one works. Okay. Do you want me to show it off to show the model, or do you want to show it, James?
Well, if you'd like. Oh no. No, I can't. Okay, let me have you do it.
Okay.
Um,
So
Are you?
Oh.
I have to stop my share first.
Yeah.
Sorry. It's the usual problem with Twitter getting messed up by Zoom.
right.
So fine
So
it looked fine on my screen, but when I go to share, it's share the file. It doesn't. It misformats the fonts.
let me do something here and here because it's kind of it's looking a little bit odd. Okay, but so the in this particular case, on the XML, we have already initialized a simulation domain that is actually not that big. It's 42 by 42 and 2-dimensional with periodic boundaries on the X and Y axis. And we have initialized a single cell called cell A. We have enabled the volume plugin. So we're gonna use the volume constraint and a neighbor tracker plugin that allows us to iterate over the cell neighbors. And this is going to be important because in the notch signaling, the notch signaling depends on the contact area between the two cells, right? If you imagine cells having receptors that interact between each other, then the strength of that interaction is going to depend on how many receptors they have and how much the surface area between the cells is. So that's why we need to keep track of what the cell neighbors are. And then we initialized basically the whole filling up the whole simulation domain. So that's just what the XML is doing. And then I'm gonna execute it so we can see what the initial configuration is, and then I'll come back to the step-out function. So when I run the model, the first thing that happens is that it appears with it shows up with the whole simulation domain filled up by cells, right? So now when I come back to the steppables, I can see that the model is being loaded. I have this delta notch steppable class that has this that defines this model file that it's a reference to a file that contains the model that James was just describing as an SPML. And maybe we can actually have a look at what that file looks, what the file looks like. Okay, so that didn't work. I was just trying to add it as a resource so we can have a look at it right here in the let's see. Okay. So here, I added it as a resource so it becomes available to me in Twitter. And what I wanted to show here was just what the SBML file looks like. This is basically specifying what the model is, what the rates is between the variables of the model, and what are the parameters that determine the dynamics between the variables. So my model file variable here is referencing the location where this SBML model is being stored. Next, what I do is that I want to load this model inside each of my cells. So in this particular case, the model is added using this add SBML to cell types. And you see that I have to specify then what the model file is, what is the name of the what the name of the model is gonna be, and what are the cell types that are gonna be assigning this model to, and again, how many SBML model steps correspond to one of my simulation steps. So before continuing, this particular syntax is a syntax that we use to load a model that is already specified as a SBML file. But as James was explaining earlier, we also have the option of loading the same model, but as an anti-money string instead of as an SBML file. But for doing that, I would have to specify what the anti-money string is. Let's call it here string, and we'll come back to what the string is later. And then I can use a different syntax to, instead of loading the SBML model, I load the anti-money string instead. And if I want to access what the syntax is, I can come to CC3D Python, SBML solver, and you'll see a bunch of options here. So I have the option of adding XML. The string that James posted in the chat is a string that it's a string of the model, but I would also show how to extract this string from the SBML file, because that's exactly how we got that one. But coming back to the syntax, I go to CC3D Python, I go to SBML solvers, and I get many options. I can those options related to SBML models, options related to cell ML models. There are another markup language, and then the options related to the anti-money models. So what we want to do is that we want to add, instead of the model, instead of adding it as a SBML model, we'll add it as an anti-money string. And then we get all of these instructions that accompany the code snippet, but now you see that the syntax is different. Instead of adding SBML to cell types, I have add anti-money to cell types. And again, I could have a file that specifies what the anti-money string is, or I could also have the specific model string that contains the anti-money model. So if I were to specify the anti-money string that James posted in the chat, I could load it into my cells. I could load it into my cells. And this, now that I have the anti-money string, I can load it into my cells by assigning a name to the model, what the cell type is that I want to assign the anti-money model to, and what the step size is with the corresponding to the correspondence between the Monte Carlo step and the anti-money model step. Okay, and what I want you to see here is that this model and these two, line 38 and 39, are equivalent. They are doing the same thing, except that one is doing it by loading it from the SBML model, and then line 39 is doing it by loading it from the anti-money string. Okay. There is an important question as how do we go from one and the other, and what are the advantages? And one of the advantages of using anti-money strings is that they are human readable, or easier to understand and read than their SPML counterparts. But there are parsers that will turn one structure into the other one, and that's what I want to show now. But before that, I want to make sure that everyone is up to date to what I've done so far. Let's see. I don't see the poll results. Okay, yeah. So everyone is with me. So yeah, good. So I relaunch for the second part, because now what I'm gonna do is show you how to go from the SBML model to the anti-money string. And for that, I use Jupyter. I'm gonna use it locally here, but you can also use the one that has Tellurium in NanoHub. Let's go here. So I'm gonna launch my Jupyter notebook locally. Oh, it's not here. Just one second. Just one second while I find out where the. So one second, because I think in the chat that you sent earlier, James, in the first version that you sent, there was the file that I needed to do this. It's not. One second. So I guess I could do it manually as well. It's not too complicated. So all I need is in the Jupyter notebook, I need to import Tellurium, which is it's a package that allows me to load and run and execute anti-money models. And then using the function SBML, and it might be like this, SBML to anti-money, I can import what my SBML is, and Tellurium is gonna give me a anti-money string version of the SBML model that we just saw. The only thing about the way it's printed into the console is that it's not very readable because it has all these line breaks. So what I usually do, typically, you can do this in any editor that you want, is that I paste the output of that function into an editor, and I replace my break lines by my slash ends by actual line breaks. And then that gives you back exactly the model that James shared earlier, which is the anti-money string that corresponds to the SBML model that is contained in this file. And again, I just wanted to point out what the syntax of the function is. Let me see what the poll says. So I want to give everyone a chance because it's not extremely complicated, but you do have to have this DN Collier SBML, right? Which is the one that we're using to load the model. And then you have to be able to, you have to have the Tellurium package installed locally if you want to run it locally. If not, you can use the Tellurium tool in NanoHub that is immediately available to you. But then once you have the clean version of your anti-money string, you can use that to load it into your cells instead of loading the. So see, this is the exact version, the exact same as what you just saw, and loading it either from the SBML or as the anti-money string are supposed to be equivalent. Then the rest of the file, the rest of the code initializes the values of delta and notch randomly on each cell from a value from 0.9 to 1. And it assigns a target and lambda volume to the cells. And then the rest of in the step function, you see that I iterate through each of my cells. And then I need to calculate this D average, which is the delta averaged over the neighbors of the cell. And what I do is that I iterate through my neighbor list, the list of all the neighbors of my cell, right? So I'm iterating through my cells. And then over each of those cells, I looked at all of the neighbors. And then I collect how much delta each of those neighbors have. And then I average that delta over the number of neighbors that I have. So basically, I'm connecting the anti-money model, right, that has this D average with a CompuCell quantity that I can identify and extract from the spatial information. And that quantity is how much delta each of my neighbor has averaged over the number of neighbors that I have. Okay. And what I'm gonna do first is I'm gonna execute this code, loading it as an SBML model. Which one is not working now? This was just working. Let me come back. I'll retype this in a second. Because this was working. I'm not necessarily sure what I did. Let me. XML element adapter. Not sure why it's not working. It was just like I just launched it. Does anyone has an a working version of the code that they want to show? Let's see. Including it could be the one with the with it doesn't have to have the anthem on the string. It would suffice to have the one with the SPML model. Anyone has a working version? List out of range.
I mean, the base model for me is like it's running, but it's not showing anything. Like
Can you screen share it? And that would be
Yeah.
helpful.
Yeah.
Because we're going to run it. We're almost out of time, but I did want to show how to save a movie because I think that's important. So if you run that, if you execute that, so you're running it on NanoHub. That's great.
right.
Open in player.
Like
Looks like player's already running, so you should just be able to switch on the bottom to player. Bottom, okay. Okay, hit run.
oh, here we go. The graph is just all the way over here.
Hit tile under window, hit tile. And why don't you create another window which is going to show delta as well as notch. And now hit tile again. Okay, and now you hit and you'll see in this one, delta and notch are opposite to each other. Low delta is high notch and high delta is low notch. And you'll notice there's some cells in the middle that get confused that are yellow that don't know which way to go. So one thing we should walk through probably is it's a little less useful in NanoHub because you get uploading and downloading files is not so much fun. You have to learn how to zip files. Is to save movies. And so if you want to save a movie, you go to the settings button, the settings button, that's the screwdriver and wrench there. And now it's doing it already where it says save image every nth Monte Carlo step. So you've got that box ticked. So you click OK. Okay, good. And now you would click the camera button next to the delta and the notch. And you could do that for the other one too. And certainly slowed it down a lot. Now, every 10 Monte Carlo steps, it's saving a picture of that image. And it'll save those as PNGs. And then depending on what your, may I screen share back just for a second to show people at the end. If I go in, this is going to look slightly different depending on what your operating system is. but this is the output of when I run that simulation. I only saved, this is the notch scalar field. And in Windows, if I want to create a movie, I would select all of these. I right click on it. You probably can't see the right click that I'm doing. And I can, under Windows, I have an option, which is the second one from the top, which is create a new video. If I click on create a new video, it's thinking for a minute. Let's see, has it done it? Yeah, okay. It's giving me a, let me try that again. It looks like it looks like it may not, interact happily with Zoom. I'm sorry. It looks like it doesn't get along. Looks like it. It looks like it may not get along with Zoom, at least on my computer. Oh, there it is. Okay, came up. Okay. So now I will screen share this. It will open this. This is Windows, and I can type the name for the video, like Delta Notch video. Okay. Then I can select all of my files here. Can you see that? I do place in the storyboard. I go to my storyboard and I select everything. I select everything. Let's see. How do I do select all? Select all. Select all is Control A. I go to duration and I type a number that gives me something reasonable at the top here. It says 5.27. If I make the duration 0.2 seconds, the movie will be 21 seconds long. And I can now play the movie. You see the movie play. And if I want to save it, I can hit finish video and it will save it. So there may be other simpler ways to do it, but that's not so bad. So you take the files, the PNGs, select them, right click, say convert to movie. You have to do a select all, add, select all here, set the time per frame, and hit finish. So it takes about a minute to make a video. Macs have a slightly different tool for doing that. And on Linux, I assume that you have to look for a tool.
Can I share something real quick, James, as well?
And then we'll wrap up because we're running over.
So I don't know what was happening with the code that I had, but so now with this one, so I have the anti-mono string defined inside my Compusol in the step hours, and then I have these two options. I either load the model and as SBML or as an anti-mono, and I want to run it first. Let's see, as a SBML model, and that's what I get. That's running it with the SBML model. And instead of doing that, I can run it as I can run it loading the anti-money string. And it's equivalent in the results. So it produces the same model, but either as an SBML or a anti-money string. That's all.
Okay.